Welcome back. So hypothesis testing in normal distributions, or at least in distributions that could be approximated by a normal distribution. Now I'm going to make a few assumptions, okay, so that you've watched, okay, and kind of understand repeated sampling. So what happens there, okay, so I'll put up a link up above, okay, to that in case you're not sure about that. And what the ultimate goal of this video will be is to give you a couple of examples of how you can test certain hypotheses or certain statements, maybe by companies, that they make. So for instance, before I get into this jargon here, if somebody gave you an example like this, okay, so let's say a chip company has placed a label on a bag of chips of 150 grams, so that we have 150 grams in each bag. The company claims that the mass of the bag, okay, or of a bag, okay, comes with a standard deviation of 2.5 grams. Now, you think that the company is cheating, okay, and decide to conduct a study by buying 50 bags. And now you find out that the average of your sample is 148.5 grams. Notice that's smaller, okay, than the 150 that is placed on the bag. Now, is your result enough to show that the company is cheating their customers? So this is the type of hypothesis testing that we want to be able to do. We want to take the original hypothesis of the company. So let's say that the mean that they're claiming is 150 grams, and that is with a standard deviation of 2.5 grams. That's their original hypothesis. And we want to state a new hypothesis. So we want to say, well, we believe that actually, okay, the bags are less than 150 grams. And, if we do take a sample, because obviously we can't measure all the different bags, okay? So we'll take a sample, and let's say you bought 50 bags, and then you get a result where your mean from the bags is actually 148.5 grams. So ultimately, this depends on what is the probabilities here that we would have a collection of 50 bags and that their mean was 148.5. Okay, so I'm going to come back to this because it's a good serving point, okay, to what we really want to do, okay, which is hypothesis testing. So we want to test something, okay, that maybe someone is making an original statement on. So the repeated sampling, okay, so why is that important? Because of the fact that we know that if you take a sample, so in this case with the bag of chips, if we have a sample of 50 of them, right, we're supposed to have a mean of about 150 grams. Okay, that's what the example stated. But there's of course a standard deviation. And now we have taken, so N in this case is 50 bags. So we know that the averages are actually normally distributed when you're taking, okay, these 50 samples, okay, or 50 data points, and they're normally distributed across the mean with a standard deviation of sigma of the original population divided by the square root of n. So that's going to be really important for us, right? And then we can find out what the probabilities are that we're actually going to be falling, okay, at whatever it was that we had there. So now, so what do we have here? We have an initial hypothesis, okay? So that initial hypothesis, so through this example, so that would have been, HI, okay, or H, so the null hypothesis, okay, so sometimes it's put as H0. So this hypothesis by the company is that the mean is 150 grams, and then that our standard deviation is 2.5 grams. That is the original hypothesis. Now we want to challenge this, so we create an alternative hypothesis. So we want to challenge or test the hypothesis. So our hypothesis that we have, so I'm going to say H alternative or H1 for the first, I guess, hypothesis. I'll just put A for alternative. We are saying that actually, the mean is probably less than 150 grams. Okay, that's what our hypothesis is. So we're testing the original one. And now, so how do we test that, right? So what probabilities are we looking for? And in hypothesis testing, you will have this concept of this threshold, or there's a significance level where you want to find, okay, so that significance level is nothing else but just simply a probability of error, okay, in your alternative hypothesis. So what is the probability, right, for us? So how much, okay, probability is there within this? So for instance, okay, if we take this, okay, so here it doesn't state anything, but it does say that is your result enough to show that the company is cheating, okay, their customers. So we really want to be testing out this hypothesis, okay, this original one, by the company making a claim on their bag, okay, by this. So now the idea is that, well, we have found, right, in 50 bags, so this is 50 bags, okay, we have found that the mean, okay, is actually equal to 148.5. That's what we have found. And now, okay, we want to be able to see, how likely could this be? So if you recall, so, here is if we have our normal distribution right here, so this is mu, so this would have been 150 grams. Now, for the samples, okay, so the standard deviation is sigma over n, right? So this is negative, and this goes both sides as so. So we have that, but we know what this is. So this is 2.5 grams, okay, divided by, this is going to be square root of 50, okay? So that is the standard deviation, okay, so on the assumption that n is equal to 50 right here, and it's normally distributed. And you'll notice that, well, this mark, okay, so this 148.5, so it's actually going to fall, so somewhere, so it's going to be falling somewhere on the left-hand side. And then the threshold is, okay, so how likely could this possibly be, right? So that threshold, okay, so this threshold level, okay, that we have, maybe, you wanted to have a threshold of 1%, okay, or 2%. So let's say, 2%, okay, within here. Now, what does that mean? That means that if we take this 148.5, now we can find out what the probability here is. This is normally distributed. So we can find out, okay, what is the probability, okay, of, okay, so this being, okay, less than 140, okay, 8.5 or equal to. What's the probability of that? And our threshold, okay, so the question mark is, within this, is it, okay, less or above that threshold? Now, if it's less than that threshold, what it means that, there is, okay, a very small probability, okay, that your sample that you have taken, okay, could have actually occurred within the entire span of all the samples. So another way of thinking about this is we actually say that there is a confidence gap. So that there is some confidence gap of 1 minus the threshold. Okay, so if you were saying, so as I said, let's say if the threshold was 2%, which is the probability of error in your new hypothesis, okay, the confidence level is the probability of being correct. So here, what you would be saying, 1 minus this, which is going to be equal to 98%. So that would mean you are confident within 98% that your result of the alternative hypothesis, okay, is actually true. It has a 98%. Now, this threshold that we set for ourselves is kind of arbitrary. But what you're looking for is how rare is, okay, the sample that you have. Like, what is the probability? How rare could that possibly be? So if it's not that rare, then you might say, okay, well, then in that case, well, maybe the original hypothesis is actually incorrect. So let's take a look and see, okay, so what happens? What kind okay, of probabilities do we have in here, okay, in terms of our statement? So let's try to see this. So if I calculate this through, now I can, of course, okay, I'm going to take out decimals here. We can find the probabilities any way we like. Let me just take out decimals in here. So what I'm going to say is this. So I have n, okay, is equal to 50. Okay, so that's what I have in there. My mean, okay, so let's say the normal, actually for this one, normal distribution. So this would have been 150, and then this is going to be sigma, which is 2.5 all over square root of 50, okay, so or of n. Okay, so if we look at this, you know, we can see, you know, how does this actually fall within here. Let's try to bring this down, okay, and span it out. So, okay, so there we go. Starts to look like what we wanted. Okay, so there it is. Notice, okay, so within this normal distribution, now what we are looking for is 148.5. What's the probability of that? And notice it's puny. It is puny. Okay? So now, what that is telling us, so 0.000011, okay, is definitely less than the threshold. Okay, so it's way less. So what this is saying is that the probability of taking a sample of 50 bags and then measuring out that you have your mean, okay, of those bags, so the weight of it, 148.5 grams, is tiny. It's extremely rare. You know, it's certainly less than 1%, certainly less than the 2% threshold that I put in here, but the threshold is kind of irrelevant. We can set it as we like it. So what does this tell us now? You know, is your result enough to show that the company is cheating their customers? Well, yes, quite likely, okay, it is, because it's extremely rare to take a sample of 50 bags and then have a mean of 148.5. It's extremely rare for that to actually happen, right? In terms of the overall thing. So for that, okay, as n is equal to, you know, 50, okay, in this particular case, and this is very rare to happen, you might say, well, yeah, you know what, the company is possibly cheating. So my original hypothesis, I have tested with my alternate hypothesis, okay, within this. And now notice that 1 minus, okay, the probability, which is, you know, 0. Okay, 0, 0, 0, 0, you know, 1, 1. Okay, this is basically 99.99 and so on %. So you have that, okay, as your confidence. Okay, this is your level of confidence in your alternative hypothesis that you're making. So you're very confident that you're going to be challenging this out, okay, within here. So that's what hypothesis testing is all about. You're just testing out how probable an alternative is. Now, when you're taking an alternative, you need some proof. So in this case, well, the proof is that you've bought 50 bags and then that you've weighed them out and then you found what the actual mean, okay, of those bags is. All right? So it's highly improbable for that to have such a small, okay, so 148.5, okay, grams, okay, for your average. So this is really interesting. So if I go back in here, that's what the hypothesis testing is all about. So I had an initial hypothesis. So in this case, you know, what was the average? What's the standard deviation for this bags of chips? I have challenged it with an alternative hypothesis. I'm saying that I think that the average is less. And then, you know, what significance level, like what probability of error, okay, in your alternative hypothesis do you have? Well, what is the probability of error? Well, our probability of error that we found, okay, within here was 0.0, you know, 00, I think it was 11. Now, of course, so this is saying like it is, you know, 0.001 of a percent. So what's the probability of error? Tiny, okay, in your alternative hypothesis. And then what is the probability, okay, of a correct decision in your alternative hypothesis? Well, then that's the opposite. That's this. And for us, that's 99, okay? So this is really like saying 99.99%. That's how confident we are in our alternative. So I would say, yeah, this company, okay, may be actually cheating their customers. We should look into this. So that's one example of how you can actually test the hypothesis. Now, these testing of hypotheses, they don't have to necessarily be in a full-out normal distribution. So I assume that was the case for this example. It could be in something different. It could be, for example, in a binomial distribution. And then remember, binomial distributions can be approximated by a normal distribution, right? So if you forgot that, I'll put up a link up above there, okay? So that was on this whole normal distribution chapter. So within here, let me get rid of this. Here's another example. So this is a beautiful example, okay? Now, the numbers here are made up, all right? So I don't want you to think that this is reality. It's just made up. But then how could we possibly challenge, let's say, someone like a pharmaceutical company? So historically, 0.8% of the population who contract the virus die. Okay, so let's say that normally happens. Now, a pharmaceutical company comes along, okay, and is testing out a new vaccine, okay, and they tested it out on 12,250 patients. And what they have found, okay, is that patients that were treated with the vaccine, 12,160 recovered from the virus within 60 days. Okay? And now you might say, oh, great. Maybe this vaccine is really good. Okay? Because if you take, so 1, 2, this is 160, let's say, divided by 1, 2, this is 250. So look at that. It's, the company can put blaring headlines and say, 99.3% effective. Okay, so within here, 99.3% effective. And then people will be going like, oh my gosh, this is an amazing vaccine. Well, but what they're forgetting is that, hey, wait a minute. Okay, without the vaccine at all, okay, you still have only 0.8% of the population that actually die. So what that is telling you, that in general, 99.2%, okay, actually just recovers. So, is the vaccine really that good? Well, we can try to test it out, okay, and see what happens quantitatively. Now, this is an actual binomial distribution, okay, within here. So let's, try to see how we could approach this. So let's say our original claim, okay, our original hypothesis within here, okay, that we have, is that, so within here, that 0.8% of the population contract the virus. So let's say, the company, okay, wants to claim with a confidence level of 99% that the vaccine is effective. Okay, so let's say that that's the original hypothesis. 99% confidence level that, okay, vaccine is effective. All right, so that's what we want. So really, confidence level, so if you recall, that's 1 minus that. Okay, so that means the threshold, okay, is actually equal to 1% or 0.01. So we want to be able to challenge this throughout. Okay, let's see what happens. How can we challenge this? Okay, so within here, so our hypothesis is that, well, we're going to challenge this company and say that, it certainly doesn't meet the confidence level of 99%, right? So let's say that's the alternative hypothesis that we're looking at. So now it is a little bit different than the previous example. So here our probability, okay, is 0.008. Okay, so I'm just changing the percent back into a decimal. So that's my probability. So within here, so n, so the total is 12250. So that's the total number of the data that we have, okay, in terms of the patients. So what I want to be able to do is, I would want to say, if I took this many patients, right, and they weren't actually treated, so they weren't treated at all, okay, so there was no vaccine, what's the probability that I would have, okay, so in this case, so this is 1,000, okay, so within here, okay, so this is 12,250, that's the total, minus 12160, okay, so the difference between them, I guess, what is that, 90, okay, so that I have 90, okay, of them actually not recovering, so passing away. So within that, so I think I did the math correctly there, 40, yeah, all right, so about 90 of them. Okay, so let's see what happens. Now, it is a binomial distribution, right? So this is binomial distribution. So I do have to be careful. I would want to model this in terms of a normal distribution. Now, if I'm modeling it with a normal distribution, so my mean, my expected value is just p, so n times p. So that's 12250 multiplied by 0.008. And then my standard deviation, okay, is n times p times 1 minus p. So that I can also find. So I'm going to do all of that. 12250 times 0.008. Okay, and this is going to be 1 minus, okay, whatever. I'm going to leave this as that, okay, for here. So now let's check this out, okay? So let's see what happens here. I'm going to use the 2 O's of decimals again. So let me shift this out. Okay, so let's clean this off. So my n, 12250. My p, 0.008. Okay. Now, binomial distribution. So you can look it up under functions. So number of trials is 12250. And my p, okay. So actually, I can just put n and p. There we go. Okay, let me zoom in here. Okay, so this is zoomed in. Now, if you remember, the binomial distribution can be approximated, the binomial distribution can be approximated by the normal distribution, but you have to be careful about the fringes, right? This is actually really to the left. But as you can see, we can certainly try to see if a normal distribution, okay, would approximate this. And it does look like so, okay, within here. Now we can calculate the cumulative probabilities, both from the binomial distribution or by the normal distribution. So I'm actually going to, try to do both here. So this is my mean, so that's NP, and then this is going to be square root of NP1 minus P. Look at that, so they do approximate. Okay, so the normal distribution does approximate this one. Okay, and it's not to the fringes too far off to the left. So we can actually use that. I can use one or the other within here, so binomial distribution. Now, we want a threshold, so confidence level of 99, okay? Well, 99, so, what are we looking for? Well, we want the probability. This is going to be, I'm going to go on the binomial distribution, and I'm going to see what the normal distribution would have approximated this by. So this is from 0 to 90. Okay, so there you go. So notice right here. So this is very interesting. So it's going to, the cumulative is 0.2255. Okay, so are we within that 1%? Okay, so within here, I mean, this is huge, right? So this actually can happen without any vaccine. So if you took a sample of, this big of a sample, right here, you certainly have, so you have about 22.5%, probabilities within here. So my threshold was supposed to be 1%, right? So, for them to make a claim, it's actually not very rare that you would find a big sample like this just in the general population, and then they would recover just on their own without any vaccine. So is this a 99% confidence gap? No, right? Because if you take this, so 1 minus 0.2255 is actually, it's almost 80%. Okay, so you only are about 80% confident, okay, within here. So this company, okay, although their claim they wanted a 99% confidence level, which means the threshold had to be just 1%. So that certainly would have not been the case. They would have had to see a lot better improvement, okay, than this. This had to be way smaller, right? And actually, let's take a look. So in here, how many, how much smaller? Let's say 45. All right. Okay. So, so let's say 50. Okay. This was 90. So let's say 80. Okay. That's 3%. Okay. So now let's say maybe 75. All right. So now that's less than that 1% threshold. So that's what they would have had to be seeing, okay, that it's very rare for 75 people, okay, to actually die in the general population. So that's what they would have had. Now in the normal distribution, if we were comparing this, so let's see within here, the maximum, so this I guess would have been 90 or 90.5, I think. Okay, because we always want to go a little bit further. Normal distribution, please remember, it's continuous. So we have to go a little bit further. So yeah, so about the same thing, right? So we said 90 here. So 22.5 or 22.6, yeah, 22, this is 0.3. So the normal distribution does actually show us that. All right, so those are two examples, pretty neat examples to be able to see, all right, how you can test certain hypotheses with sample spaces, okay, within. Okay, so thank you for watching, and we will see you in a future video. Bye, everybody.